Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 52 on Convergence Tests, Part 2.
One of the first series that we saw in this course was the geometric series. In this lesson, we're going to leverage our understanding of the geometric series to provide us with two additional tests for series convergence. These are the root test and the ratio test.
There is one series whose convergence and divergence we understand well. Indeed, from the very beginning of this course, we have understood the geometric series and when, precisely, it converges. We're going to use that as the basis for two convergence tests for more general series. The first of these tests is called the root test. It goes as follows. The hypotheses are very minimal. We just need a positive sequence, a sub n. From that, we compute the following quantity, rho, defined to be the limit as n goes to infinity of the nth root of a sub n. The test is as follows. The series sum of a sub n converges if rho is less than 1. If rho is greater than 1, then the series diverges. Now you might wonder, what happens if rho equals 1? Haha, the test fails. It says nothing in that case. Now, as far as applicability, why, this is a very general test. It applies to almost anything. Its ease of use, well, it depends. Computing the nth root and taking a limit as n goes to infinity, that can be a little difficult, and that limits the usefulness of this test. However, when it does work, it does what other tests usually cannot do. Let's see some examples. Consider the sum n goes from 1 to infinity of quantity log of 1 plus cosine 1 over n, all raised to the 1/2 n power. That looks very difficult with regards to comparisons or integral tests or anything of that sort. However, if we apply the root test, then we compute rho, the limit as n goes to infinity of the nth root of a sub n. Since a sub n involves an exponent with an n in it, this nth root cancels that, and we're left with the limit as n goes to infinity of the square root of log of quantity 1 plus cosine 1 over n. Well, we can evaluate that limit. As n goes to infinity, cosine of 1 over n is tending towards 1. Therefore, rho is equal to the square root of the log of 2. That is definitely less than 1, and that means that this series converges. Was that obvious to you from the beginning? Wasn't obvious to me. Well, here's another example. Let's look at the p-series, where a sub n is 1 over n to the p for some constant p. In this case, when we compute rho, what happens? Well, we see some of the limitations of the root test. We need to compute the limit as n goes to infinity of the nth root of n, and then raise that to the minus pth power. Well, that limit of the nth root of n is equal to 1, and 1 to anything is 1. This test fails for the p-series. Of course, this must be the case because depending on the value of p, the p-series either converges or diverges. In this case, the root test doesn't tell you. Now, the reason why the root test works is through a comparison to the geometric series. In the geometric series, a sub n is really x to the n. And we see that in taking the nth root, if we get something that eventually behaves like a geometric series, that is, where the nth root of a sub n is tending to a number that is less than 1, then we get convergence. But there's another way that we could use the geometric series as well. What if, instead of looking at the nth root of the nth term, we looked at the limit, as n goes to infinity, of the ratio between subsequent terms? For the geometric series, a sub n plus 1 divided by a sub n is really x to the n plus 1 divided by x to the n, that is x. We expect similar types of results with this ratio. Indeed, that is the basis of the ratio test. If, as before, we have a positive sequence and we compute rho, this time to be the limit as n goes to infinity of a sub n plus 1 over a sub n, then the exact same conclusions hold. When this quantity is less than 1, the series converges. If this quantity is greater than 1, the series diverges. Now, this is a test. This test tends to be extremely easy to use and extremely useful, so much so that for most series, the ratio test should be your first choice. Let's see a few examples. Consider the sum, n goes from 0 to infinity, of n factorial cubed over quantity 3n factorial. Now, this could look a little bit confusing. Does this converge? Does it diverge? Well, let's see what the ratio test has to say. In this case, a sub n equals n factorial cubed over quantity 3n factorial. A sub n plus 1, well, we have to be careful when we're doing factorials. This is n plus 1 factorial quantity cubed over quantity 3n plus 3 factorial. Now, when we compute rho, that is the limit of the ratio, remember, it's a sub n plus 1 on top, a sub n below. We can evaluate this by multiplying a sub n plus 1 times the reciprocal of a sub n. When we do so, because of these factorials, there's a great deal of cancellation. The n plus 1 factorial cubed cancels with the n factorial cubed, leaving just an n plus 1 quantity cubed. Likewise with the 3n factorial and the quantity 3n plus 3 factorial, we are left with the limit as n goes to infinity of n plus 1 quantity cubed over 3n plus 3 times 3n plus 2 times 3n plus 1. The leading term is cubic in n and cancels in the numerator and the denominator, yielding 1/27. That is much less than 1, and we have a convergent series. Here's another example. Consider the sum of n to the n over n factorial. Well, you might be able to argue, based on what you know about n to the n, that this diverges. That's certainly what I would guess. But let's say we needed to show that explicitly. Well, we could try the ratio test. Let's see what we get. A sub n is n to the n over n factorial. A sub n plus 1 is n plus 1 quantity to the n plus 1 over quantity n plus 1 factorial. When we compute this limit, rho, we get n plus 1 to the n plus 1 over n plus 1 factorial times n factorial over n to the n. As before, there's quite a bit of cancellation going on with these factorials, and we're left with the limit as n goes to infinity of n plus 1 to the n plus 1 over n plus 1 times 1 over n to the n. There's some canceling that goes on there. And what do we get? We get, after a little bit of rewriting, a limit that we've seen before. The limit as n goes to infinity of quantity 1 plus 1 over n all to the nth. That is e. That means the ratio of the subsequent terms tends to a number that is bigger than 1. That is precisely e. That means this series diverges, as we thought. Now, sometimes it's not clear exactly which test ought to be used. Consider the following complicated-looking series. You've got odd numbers in the numerator and the product of even numbers in the denominator and 1 over 2 to the n. What do we do? Well, let's try the ratio test. In this case, a sub n is the product of odd numbers up to 2n minus 1 divided by the product of even numbers up to 2n with an extra 1 over 2 to the n in the denominator. When we substitute in n plus 1, we have to up the index on all these terms. But notice the amount of cancellation that happens when we compute the ratio of a n plus 1 to a n. After all of that cancellation, we're really only left with just a couple of terms. That would be 2n plus 1 in the numerator and 2 times quantity 2n plus 2 in the denominator. The leading order terms in numerator and denominator are 2n and 4n respectively. That yields a limit of 1/2. Therefore, this series converges. It converges to something very nice. You'll learn to what soon. Sometimes it's not always clear which test is going to be best. Consider the sum as n goes from 0 to infinity of pi to the 2/3 n divided by e to the n times n factorial. What is this going to be? It seems like it ought to converge. Let's see. We could try the root test. The root test tends to work when you have something with an exponent that has an n in it. Let's see what happens if we take the limit as n goes to infinity of the nth root of pi to the 2/3 n divided by e to the n times n factorial. Well, that pi term and the e term work out nicely. But we're left with pi to the 2/3 over e times the nth root of 1 over n factorial. That is maybe not so easy to do. If you want to get fancy, then we can use Stirling's formula for the asymptotics of the factorial. Well, I don't know. I'm not really in the mood for that. I'm not quite sure how to evaluate that limit. So let's try the ratio test. Instead, we take a sub n plus 1, multiply by the reciprocal of a sub n, and take the limit as n goes to infinity. Well, this one works, and it works well. We see that rho, this limit, is equal to 0. That means that not only does this series converge, but the terms in the series get small very, very quickly. Now, if we had thought about that, we would have said, well, of course, that's true. N factorial grows much, much more quickly than pi to the 2/3 n. So certainly this must converge. On the other hand, if we had been thinking from the beginning, we might have noticed that this series is actually of the form sum 1 over n factorial times something to the n. That means we're really looking at our old friend e to the x in series form, evaluated at x equals pi to the 2/3 over e. Once you start doing convergence tests, don't forget to think. Now, there are many tests that you have at your disposal. Use them. Learn which test tends to be best with which type of series. And then, like a collection of keys, keep trying until you unlock the convergence.
This concludes our principal set of tests for determining convergence and divergence of infinite series. At this point, it would be a good idea to do a lot of homework problems so that you gain an intuition for which test works when. Just like with integration, not every method is useful in all circumstances. In our next lesson, we're going to introduce a new class of infinite series and refine our notions of convergence.